I'm Jeff Groh, and this is Partial Differential Equations. Today, we're going to talk about the elements of Fourier series, or Fourier series. Last time, we looked at solutions to the wave equation, and we found solutions of the form the sum as k goes from, say, 1 to infinity, a sub k sine of k times pi over L times x cosine c k pi over L times t. A series involving sines and cosines. We're going to see how far we can go with this today. First, I'd like to recall a few terms from linear algebra. Recall that a linear combination of vectors in a set S, I'm allowing S to be any subset of a vector space, is a sum of the form C1v1 plus CKVK, where each of these V's is an element of the set, and that set is a subset of the vector space, so each of these are vectors, and C1 through CK are scalars. I'm allowing these scalars to be real numbers, for instance, if the field over which the vector space is defined is the real number system. It can also be complex numbers, or it could be elements out of a different field. But we're not going to get too far into the algebra here. We're just going to talk about scalars. What I'd like to emphasize about an expression of this form is that the sum is finite. Every linear combination is merely a finite sum. We do not allow linear combinations to be infinite sums. Those are going to be infinite series. Linear combinations are finite. Also, a set S is called linearly independent if whenever V1 through Vk are an S, and we have a linear combination C1v1 through CKVK is the zero vector within a vector space, then all of the coefficients are zero scalars. The only way you can get a linear combination that adds up to zero is the trivial one, where all of the coefficients are zero. If the coefficients are zero, you clearly will get zero, regardless of what these vectors are. The trick is, that's the only one. In addition, what is a basis? Now, there are different kinds of bases. A Homo basis. A Homo basis is what you usually learn about in an introductory course in linear algebra. It's a linearly independent spanning set. I guess I haven't defined what I mean by span, but we can do that here. We say that a set S spans a vector space V. Every element of V may be expressed as a linear combination of elements of the set S. So everything in V can be constructed from elements in the set S. Notice that there are two elements to be a basis. The basis must be linearly independent, and it must span the vector space. There are classical examples. On R2, a basis might consist of 1, 0, and 0, 1. And on R3, a basis might be 1, 0, 0, 0, 1, 0, 0, 0, 1. And on Pn, the set of polynomials of degree n or less, a basis might be 1, x squared to x to the power n. Notice that this basis has n plus 1 elements, and therefore the dimension of the vector space of polynomials of degree n or less is n plus 1. Every basis has the same number of elements, and we define the dimension of a vector space to be the number of elements in a basis. That's why R3 has dimension 3, and R2 has dimension 2. Notice that the vector space of all polynomials has a basis that goes on forever. In other words, the vector space of all polynomials is infinite dimensional. So we're going to allow for that possibility, that we could be working with infinite dimensional vector spaces. What is an inner product? Let V be a vector space over R. We're going to deal with real inner products and real vector spaces. The set of scalars we're assuming for the vector space V is the set of real numbers. An inner product on V, it's a function. It has two input slots. It maps V cross V, so it takes vectors and plugs them into these two spots and outputs a real number satisfying the following properties. First, if you take the inner product of a vector with itself, you must get something that's non-negative. And what is more, if the inner product of a vector with itself is 0, it follows that the vector is the 0 vector within the vector space. Real inner products satisfy the following symmetry property, kind of a commutative law for multiplication, if you will. When you take the inner product of u and v, you'll get the same thing if you take the inner product of v and u. Now, when you introduce a new operation on a vector space, you have to explain how that operation works with respect to the operations that already exist on that object. In this case, scalar multiplication and vector addition. So there has to be two more properties. The inner product of a constant c times u, a scalar c times u, will give you the same thing as if you put the scalar on the other coordinate, and that gives you the same thing as if you factor it out. This is a kind of associative property, if you will, where you can associate the scalar with either of the factors in the product or outside of the product like that. And the fourth property for an inner product is that if you have u plus v, w, that's the same thing as the inner product of u with w plus the inner product of v with w, giving you a kind of distributive law for the inner product. As an example, the Euclidean dot product is an inner product. When you dot a vector with itself, you get something non-negative. And since u dot u is the norm squared, if that is equal to 0, that's true if and only if u is the 0 vector. U dot v is v dot u. Any scalar factor can be put on either of the two factors. And if you have u plus v dotted with w, you can use kind of a distributive property. So the Euclidean dot product that you all learned about in various places, including Calculus 3 and Pre-Calculus, is an example of an inner product. Another example suppose I'm taking two functions, f of x and g of x, an inner product may be defined by the integral from 0 to 1 of f of x times g of x. You can see clearly the inner product of f and g is the inner product of g and f. What might be less clear is that first property. And one reason that this may be not quite so clear is that you can have a function on the interval 0 to 1, which is 0 except at one point, and maybe non-zero at that other point. The integral, even if you square it, is going to be 0. However, we can make an equivalence relation between functions so that if these functions differ on no more than a set of measure 0, we'll just pretend the functions are the same. They're in the same equivalence class. So let's deal with equivalence classes of functions, and when we do that, when they differ on no more than a set of measure 0 and a single point, we'll surely have measure 0 in the usual measure placed on real numbers. I know we're going a little bit outside of this course in the sense that measure theory is usually covered in a graduate course in real analysis. However, I'll assume that you can agree that on a set involving a single point, the integral will cast an area of 0, and so this will have be a set of measure 0 differing from the set that is identically 0 across the entire interval only at that one point, a set of measure 0. They'll have the same integral. And so this will be equal to 0 if and only if f is identically equal to 0, except maybe on a set of measure 0, in which case it's in the same equivalence class, and we'll pretend they're the same function. All right. Now, notice also that if you have a scalar times fg, the scalar will come out, giving you the scalar times f, the inner product of f and g, etc., etc. It's easy to check. All of the properties of an inner product are satisfied, but you have to guarantee equivalence of functions that differ on no more than a set of measures 0. There is a kind of integral for which this kind of accounting on sets of measures 0 giving you equality makes more sense than the usual Riemann integral that many of you have learned about in Calculus 1. In particular, there's something called the Lebesgue integral, that is commonly discussed in the graduate course in real analysis. However, we're not going to go into the details here. We'll just assume that you can agree that there is a kind of integral where functions that differ on a set of measure 0 may be pretended to be equivalent or in the same equivalence class, and we'll allow then for this to be a true property. I should also point out the similarity between this inner product and the Euclidean dot product. Recall that if I have x1, x2, and I'm dotting that with y1, y2, that's x1, y1 plus x2, y2, or a sum, in this case as k goes from 1 to 2, of xk, yk. In this way, I'm adding up values of these two functions, where k is the argument of the function. We're plugging k in and outputting some number that goes into each of these coordinates. Well, in an infinite dimensional vector space, the k's might need to come from a set that's bigger than the natural numbers. What if we allow those k's to come from some entire interval? Well, x's in this case. They're like the indices down here. You plug in the number, it outputs a value. You plug in the k, it outputs a value. It's the same exact thing. But when you have so many things to add up, a huge interval of things, the way to add them up is by an integral instead of the old-fashioned sigma sum. Every inner product gives rise to a norm. The norm that comes from an inner product will be defined to be the square root of the inner product of the vector with itself. In addition, every norm gives rise to a metric, which is a notion of distance. The distance between u and v is the norm of u minus v. So inner products give you a notion of distance intermediately through this notion of norm in this way. In addition, every inner product gives rise to a notion of angle. We make the following definition. The cosine of the angle between two vectors is the inner product divided by the product of the norms. This allows us to define geometry, both length and angle, once we have imposed an inner product. So you can change the geometry, the notion of length and angle, by changing what you use for your inner product. You can even do this on R2 and R3. So for example, I can define the inner product of UV to be U transpose MV, where I'm assuming M is a symmetric, so its transpose is equal to itself, and positive definite, so that X transpose MX is bigger than or equal to 0 for all X. This is positive definite. Oops. Greater than 0 when X is not the 0 vector. An example of such a matrix M might be 2, 0, 0, 3. This will give rise to a different notion of length and angle than the usual Euclidean dot product. For the Euclidean dot product, M is the identity matrix, which is clearly symmetric and positive definite. As an example, let's suppose that U is the function that is identically 1, and V is the function 2x minus 1. What is the angle between these two functions using the inner product that we defined earlier? You can see then the angle will depend upon the inner product. So we have to calculate the inner product first. So that'll be the integral from 0 to 1. It's the function 1 times the function 2x minus 1, which gives you x squared minus x. Evaluated from 0 to 1, you plug in the 1, you get 0, you plug in the 0, you get 0. Ooh, what does it mean that the numerator is 0? You can easily check that when you calculate the norm in the denominator by integrating 1 times 1, you get something other than 0 in each of those denominators. So it's 0 divided by something non-zero, which means the ratio will be 0. For what angles is cosine theta equal to 0? And the answer is assuming that angles between vectors are always numbers between 0 and pi, or 0 and 180 degrees, vectors can't be more than 180 degrees apart because you always take the smaller of the two angles as defining the angle between two vectors. We get 90 degrees, or pi over 2 radians. Ooh, so these two functions lie at a 90-degree angle between each other. You might begin to wonder, how many different functions are pairwise orthogonal? Yeah, these two functions are orthogonal to each other because they have a 90-degree angle between them. But surely you can construct other functions that are at 90 degrees to these. You can see that in an infinite dimensional vector space, which the vector space of polynomials is, you might be able to construct a whole bunch of different functions that lie at 90 degrees to each other. Yeah, more than just 3 orthogonal directions that you have in R3. You can have an infinite number of different pairwise orthogonal directions in the vector space of polynomials. The L2 inner product is the inner product that we've just described. It can be defined on any number of different potential intervals, in which case the integral goes from a to b. We're assuming here that L2 is dealing with real-valued functions. It's possible to deal with complex valued functions, in which case we have to redefine this a little bit. We'll take the integral from a to b. We'll assume the domain is real still, but we can potentially output complex numbers. We'll use the complex conjugate of the second factor, in which case the original L2 inner product for real-valued functions was bilinear. It's a linear transformation in both coordinates because the scalars can pull out of either coordinate and you can distribute across either coordinate. This is called sesquilinear, which stands for 1.5 times linear. And it's not exactly a bilinear inner product anymore. It's going to be it's not going to satisfy all of the properties that we saw earlier. It will do the following. Now, when you reverse the order of the product, you don't get exactly the same thing. You get the complex conjugate. And that's because you're switching the direction that you're putting the conjugate. Also, when you take the complex conjugate of the complex conjugate, it puts it back and gives you the thing without the conjugate. It undoes it. So this is one of the differences that you'll see with respect to these sesquilinear products. Now, you learned in Calculus 3, Pre-Calculus, and Linear Algebra how to calculate the projection of a vector u onto a vector v. The notation uses v as a subscript, and it's defined as follows: uv divided by the norm of v squared times v. All of this out front is scalar valued. The inner product is always scalar valued, as is the norm, but we're rescaling the vector v. So we're projecting u onto v in an orthogonal way. The projection of u onto v ends up down here, and this is exactly how you calculate that. We're going to do that in these infinite dimensional vector spaces as well. You might recall something called the orthogonal complement. This is the projection of u onto v. The orthogonal complement of u on v is over here, and it's easily calculated to be u minus the projection of u onto v. Notice this should be orthogonal to the vector v, this orthogonal complement right here. And we can easily check that. We'll take the inner product of v with the orthogonal complement of u on v. The orthogonal complement was u minus this projection. The projection of u on v was the inner product of u with v over the norm of v squared v. And so when we break this up, we'll get the inner product of v with u minus all of the scalar will come out. We'll have the inner product of u with v, norm v squared, and then the inner product of v with v, which is norm v squared. By definition, and hence we get 0, meaning these are orthogonal vectors, having a 90-degree angle between them, or pi over 2 radians. I'd like to also remind you of the Gram-Schmidt Orthonormalization process. Whereby you start with a bunch of vectors that are linearly independent. You set v1 to be u1. Why not? v2 is going to be u2 minus the projection of u2 onto v1. You'll get something orthogonal, the orthogonal complement. How do you get v3? What you do is you take u3, which has to be linearly independent from u1 and u2, so it has to point in an independent direction, but you're going to subtract out the projections onto v1 and v2. So you subtract out projections onto these other two orthogonal directions. You keep on constructing these new vectors by subtracting out projections from the old vectors. These vectors that you get will all be orthogonal to each other, but they won't necessarily be normalized. They won't be orthonormal. So what you do is you set W1 to be the normalization of V1. W2 is the normalization of V2, and so on. That way, you can start off with a linearly independent set and construct from it an orthonormal set. We're almost ready to do some math. First, I need to define what I mean by a Schauder basis. A Schauder basis is always, at most, countably infinite, which means that the number of elements has a one-to-one association and onto association with the natural numbers. There's a first element in the list, a second element in the list, and so on, all the way through the entire list of natural numbers. That's what it means to be countably infinite. We say that this is a Schauder basis for a vector space V if for any vector in the vector space there exist scalars Ci, I equals 1 to infinity, such that in the limit as n goes to infinity of V minus the sum as I goes from 1 to n of Ci Vi, you get 0. So you can see the distance between any given vector and some linear combination of vectors in the Schauder basis will give you 0. In this way, V may not be a finite sum of elements in the Schauder basis. It may take an infinite limit in order to construct the entire value V. Now, when this happens, this, by meaning even if we don't have a Schauder basis, we'll say that V is the sum as I goes from 1 to infinity of Ci Vi. It's a Schauder basis if you can make this construction for any vector V in the space. Even if this is not a Schauder basis, you might be able to make such a construction, in which case we'll say that we get equality with this infinite sum. You can see how a Schauder basis might be more important in physics and engineering and many mathematical applications than a Homo basis, where the sum is always finite. We're now ready to define what we mean by a Fourier series. Let En be an orthonormal sequence in a vector space V. A convergent series of the form the sum as n goes from 1 to infinity, we'll say Cn En is a Fourier series. So that's all it takes. Just have to have an infinite sequence of orthonormal vectors in some vector space. You can form a convergent series of this form. That's a Fourier series. Note, if some vector u is the sum, as n goes from 1 to infinity, of Cn En, where En is our orthonormal set, what happens if you take the inner product of u with, say, E sub k for some fixed k? Then most of these inner products, the inner product of ek with most of these ens, will be 0. The only one that will survive most of these are 0. The only one that will survive is when you have E1 with E1. But since we're assuming that these ENs form an orthonormal basis, when you take the inner product of EK with EK, you'll get 1. Well, that tells us what these constants are. We deduce that if U is expressible as a Fourier series, then we know what these coefficients are. They're the inner product of U with En. This gives us a simplified way of constructing a vector U in these orthogonal directions once we have an orthonormal Schauder basis. I should also note it is entirely possible that U does not equal the sum as n goes 1 to infinity inner product of U with En. So in other words, some vector may not be equal to its Fourier series representation. I would like to consider as an example, say L2, 0, 1, and my hypothesized Schauder basis will be 1 cosine 2 pi nx sine 2 pi nx, where n goes from 1 to infinity. We'll have an infinite number of elements in this hypothesized Schauder basis. The L2 inner product is the integral. Let's take the inner product of 1 with cosine 2 pi nx. That will be the integral from 0 to 1 of 1 times cosine 2 pi nx. Now remember the period of, say, cosine bx, the period formula is 2 pi divided by b. So the period in this case is 2 pi divided by 2 pi n. That means there are n periods inside of the interval 0 to 1. To calculate the number of periods, you take the length of the interval, which is 1, and divide by the period to get the total number of periods that fit. Well, if you integrate cosine over 1 period, you get nothing. If you integrate cosine over 2 periods, you get doubly nothing. So if you integrate cosine over n periods, you get nothing. Now the vanishing of this inner product says something geometric about these two functions. It says they're orthogonal to each other. They form a right angle. This is actually an infinite list of orthogonalities because we get a different function for each n that lies in the set of natural numbers. So we have an infinite number of different vectors that are orthogonal to the vector 1. Well, Are these cosines orthogonal to the sines? Are the different cosines orthogonal to each other for different values of n? Are the sines orthogonal to each other for different values of n? We need to check that. Before we can check the orthogonality of the other functions, we need to recall some basic identities, the product to sum identities. Cosine A, cosine B is 1/2 cosine A minus B plus cosine A plus B. Also, the sine of A, sine of B is 1/2. This time, the only difference is that we have a minus. And sine of A, cosine of B, the difference here is we do the sine of A minus B plus the sine of A plus B, which is easy to prove using the sum and difference of angle identities for cosine and for sine. Let's look at the inner product of the cosine of 2 pi nx and the cosine of 2 pi mx, where I'm specifically assuming that n and m are not equal. So we'll get the product of these two, and that's where the product to sum identity comes in. We'll get 1/2 the integral from 0 to 1. First of all, when we subtract these two, we can factor out the 2 pi x. We'll have n minus m times x. And then it's going to be plus 2 pi n plus m times x. Keep in mind that n and m, we're assuming, are elements of the set of natural numbers, which means n minus m will be an element of the set of integers. It could be negative. So what about the period? It'll be 2 pi times the absolute value of n minus m underneath 2 pi. Well, this gives us an integer number of periods within the interval 0 to 1, because again, to calculate the number of periods that you cycle through between 0 and 1, you take the length of the interval and you divide by the period. 1 over 1 over inverts and gives you the absolute value of n minus m periods, which is an integer number. If you integrate cosine over an integer number of periods, you have to get 0. And the same is true for the other term. You'll have to get 0 there because you're cycling through an integer number of periods, which means they're orthogonal. So if you choose different values for this coefficient n, then you get orthogonal functions. If you replace cosine by sine, the only thing that changes is the plus becomes a minus. So different sine functions for different values of n are orthogonal to each other as well. That leaves only one other case, the cosines and the sines together. Are they orthogonal? We'll need to take the inner product of the sine of 2 pi nx and the cosine of 2 pi mx and see what we get. Of course, it looks like a product to sum identity coming on. This is the moment for which you learned the product to sum identities, or perhaps go back and learn now if you didn't. You can see that we'll get the sine of 2 pi n minus mx, the sine of 2 pi n plus mx. And once again, the period here, absolute value n minus m, you get 1 over the absolute value of n minus m for the period, which means that we get an integer number of periods on the interval 0 to 1. And of course, for sine, if you integrate over one period, you got nothing. So if you integrate over an integer number of periods, you get that integer number of nothings. So the inner product is 0, which means if you take a function from this class and a function from this class, take their inner product, you must get 0. They are orthogonal. So this class of functions is orthogonal. However, it is not normalized. How do you calculate a Fourier series if your Schauder basis is not normalized? Well, that's not too hard to do. What you do is you take the sum as n goes from 1 to infinity, you normalize after the fact. Inner product of u with en over en. And this will give you, divided by the norm squared, you take one of those norms and normalize the en here, the other norm and normalize the en over here. So you normalize after the fact, if you will. And this is one way of coming up with a Fourier series representation of some vector on some infinite dimensional vector space. As long as this set of ens is orthogonal, that's good enough. So, what is the inner product of 1 with 1? That one's easy. You'll get 1. So this one's normalized. What about the others? We're only interested in the case where these n's are the same in this case. Cosine squared 2 pi nx is the integrand this time. And whenever you're integrating cosine squared, you need a half-angle identity. We'll have 1 plus the cosine of 4 pi nx. This last term will give you a value of 0 integrating over an integer number of periods. And so you can see we get 1/2. For sine, the only thing that differs, if you put the sine and sine here, you'll have sine squared. The only thing that differs is you get a minus here, but that term integrates to 0 anyway. So both of these will have inner product with themselves of 1/2. So when we have that denominator, inner product of en with en, we'll be dividing by 1/2, same thing as multiplying by 2. When I teach this topic, I like to use a function that is the basis for the digital revolution, say a function that is 0 between 0 and 1/2 and 1 between 1/2 and 1. So in this particular function, we start off at 0, we end up at 0 at 1/2, and then we jump to a height at 1 until we get to 1. Notice that I'm maintaining the value of 0 at 1/2. That'll come up in our analysis. So I want to take the projection of this function onto each of these orthogonal directions, and to do that, we need these inner products. This one's easy. I just integrate from 0 to 1 this function f. And that has an area of height times width. The width is 1/2 and the height is 1. So I get 1/2. Now, let's project our function f onto cosine 2 pi nx. Since this function is 0 until you get to 1/2, we may as well integrate from 1/2 to 1. And then f is 1 after that, so we're just going to have an integrand of cosine 2 pi nx. Well, what does that equal? When we integrate cosine, I'm going to get 1 over 2 pi n times the sine 2 pi nx evaluated from 1/2 to 1. When you plug in 1 for x, you're evaluating sine and an integer multiple of 2 pi, which is 0. When I plug in 1/2, the 2's will cancel and I'll still be evaluating sine and an integer multiple of pi, which is 0. So this function is orthogonal to all of those. Taking the inner product of f with the sine 2 pi nx, again, we pick up nothing until we get to 1/2. And then it's just going to be integrating sine. Using the fundamental theorem of calculus, we'll have negative 1 over 2 pi n, and then cosine 2 pi nx. When we plug in 1, we get an even multiple of pi, 2n times pi. Sine at any even multiple of pi will have a value of 1. When we plug in 1/2, we get cosine of pi n, but cosine of pi n is negative 1 to the power n. So those are the projections in this case. Now, how do we then find the Fourier series representation of this function? All we have to do is add up these values divided by the inner product of the function with themselves. Now, how do we find the Fourier series representation? We have to follow the pattern for a Schauder basis that is not normalized. Notice I'm going to put a little question mark here. Is it really, well, the inner product of 1 with f was 1/2. We have these inner products, but we divide those by the inner product of sine with itself, which was 1/2. And that gives negative 1 over pi n times 1 minus negative 1 to the n times the basis function, which was sine of 2 pi nx. Question mark. Can I really reconstruct this digital square wave by adding up sinusoidal waves in this way? This is the basis for the digital revolution, after all. All of your electronic devices are based upon this representation for this digital square wave. Let's see how well we do. I'm going to define my function x maps to, the first term was 1/2, and then we did the sum. We had negative 1 divided by pi times n times 1 minus negative 1 to the power of n times the sine of 2 times pi times n times x. I'm going to have n go from 0 to 10 to begin with. And I'm going to plot this function g of x, which may or may not be close to f of x. I'm going to go from 0 to 2. I'm going to set my view frame to go from 0 to 2 on the x, from negative 1 to 2 on the y. It's going to have the same scale on the x and the y axes. Thousand points will be the basis for the plot, and we'll make the thing in black. Yes, 1 to 10 that is. And there we have it. We have something that looks a lot like a digital square wave, but the wave has been constructed with these sinusoidal waves. These sinusoidal waves, with varying amplitudes, being combined together, yielding something that looks a lot like digital square waves. This is the basis for the digital revolution. You can construct things that approximate square waves using harmonic oscillators. Now, what happens if we change this 10 to 20? Remember, this n is supposed to go to infinity. We get something that's even better, but we still get this weird jagged tooth at the end. This illustrates something called the Gibbs Phenomenon. You can theoretically demonstrate that you get about a 9% overshoot this way and 9% this way, so 18% error in the limit. If it's 100, or well, 1,000's quite a lot. If it's 100, what do we get for the graph? You can see an even better approximation, but we still get the jagged Gibbs phenomenon at the endpoints where we have this overshoot. Notice also that the original function f was defined to be 0 at x equals 1/2. All of our approximations travel through y equals 1/2, which means that in the limit, as n goes to infinity, the limiting function for the g must go to 1/2. Also, theoretically, you can show that whatever you have on your function's limit as you go to the left and limit as you go from the right, whatever you get for those two values, you will end up with the average of those two values in the limit for your Fourier series. So the Fourier series should theoretically converge to the average of 1 and 0, i.e. 1/2, which means that pointwise, the Fourier series representation of our original function will not be the same as the original function. It will differ at this one point. Our function was defined to be 0 at x equals 1/2, not 1/2 at x equals 1/2. But in our norm L2, in our L2 norm, it can't detect the difference on a set of measures 0. So what happens at x equals 1/2 is irrelevant. And we can see that to within some set of measures 0, these functions will end up being the same in the limit as n goes to infinity, which means we will in fact have reconstructed our original function by putting together projections onto these orthogonal pieces. These are the coefficients of the projection onto these vectors of the original function. So we can convert, we can describe a street map of how to reconstruct our function by going so far this way and so far that way, turning at 90 degrees at every single corner to figure out how far to go in a particular orthogonal direction. It's like following a street map to reconstruct the function. Go this far in this direction, and then so far in the next orthogonal direction, etc. And eventually you end up at the function itself. What happens if we try 1,000? We may as well try. We get something very close indeed. To detect much difference, we may have to use more points, say 10,000 points. It'll take a little longer for the computer to give us an answer, but still, you can see that Gibbs phenomenon at the endpoints. Point-wise, we may not reconstruct the original function, but in the L2 norm, it looks like we will be able to reconstruct the original function using our orthogonal collection of basis vectors in a Schauder basis, not a Homo basis.